Alright, greetings everybody. Today we're going to talk about the electric field. Hopefully some of you recognize this picture. It's from the Boston MOS, their lightning show. It's pretty cool. You should go check it out if you've never seen it before. So we're going to start today with an analogy. The electric field is the space around an electrical charge, just as the gravitational field is the space around a mass. There's also another very important similarity, which we'll get to in a little bit, between the electric field and the gravitational field. We all remember Newton's law of universal gravitation, force of gravity, force of gravity equals big G m1 m2 divided by the radius squared. Keep this in mind because it's important later. So, as I said, the electric field is the space around a charge. It's represented by these field lines. So what's the difference between these two? Well, one's positive, here's a proton, and all of its field lines move outwards. That's why it's represented by an arrow pointing away from the proton. But in the electron, they're all going inwards. Also, the spacing between these lines is also important. The closer together these lines are, the stronger the electric field is. So if I had a whole bunch more lines drawn in here, equally spaced, imagine these going all the way around, then it would represent a stronger electric field than the one shown. And here we have a Van de Graaff generator, which is what the MOS uses in their lighting show, just a really freaking huge one. How they work is you have this metal sphere here, and you have this belt. It's like a conveyor belt that goes up on one side and down on the other. And what this does is it draws electrons from down here from some like charge source, moves them up into the metal sphere, and then it creates like a negatively charged field, and then these charges can then dissipate and they'll shoot over to like whatever's nearby. And I will show you this in class, hopefully, if I can get our Van de Graaff generator to work, and I'm going to try to shock some of the people in the class, probably the females, because they have longer hair and it'll stand up cooler than the guys will. So electric field is a vector quantity represented by a big E. And here's our first equation. E equals the force divided by Q. Now, as Q prime is the positive test charge. Q prime is always positive. For a test charge, we always use a positive charge. Always positive. E, as I said, is a vector quantity. Sometimes maybe in your book you'll see with a line over it, or you'll see like a bold E. Anytime it's a bold letter or has a line over it, that means it's a vector. The units are newtons per coulomb. Coulomb. And it's analogous to the gravitational field, where gravity, the acceleration due to gravity, equals the force divided by mass. Same difference. You know, we can rearrange this as force equals mass times gravity. You can also rearrange this to be force equals E times the test charge Q. So here's the first example. A charge of 3 microcoulombs. If you don't know what a micro is, 1 micro equals 1 times 10 to the minus 6. So if I had 1 micrometer, it'd be 1 times 10 to the 6 meters, 10 times 10 to the minus 6 meters. So a charge of 3 microcoulombs is used to test the electric field of a central charge of 6 coulombs that causes a force of 800 newtons. What is the magnitude of the electric field? So this one should be pretty easy. Where are my notes for this? I don't know. Guess we just have to fly off the cuff of this one. Alright, so our test charge is the 3 microcoulombs. We're going to convert that into coulombs. So our charge, our Q prime, equals 3 times 10 to the minus 6 coulombs. And our equation is E equals F over Q prime. So we plug stuff in, 800 newtons divided by 3 times 10 to the minus 6 coulombs. And let me find a calculator. 800 divided by 3e minus 6. And we get a huge electric field of 2.67 times 10 to the 8. That's newtons per coulomb. Hopefully I did that right. I'm not going to embarrass myself here. Yeah, I did it right. So there's your answer. These are pretty easy, 3 variable problems. They get harder. I also have this cool little electric field simulation here. It'll take you to a website that uses Java, even though Java is terrible. Let's see, electric field, electric field, electric field, electric field. Motion of charge, electric and magnetic fields. I think that's it. Oh no, electric field from a point charge. And I'm sorry I didn't have this loaded before. Please feel free to skip ahead in the video until it reaches the proper portion where this actually comes up. Yes, I accept the risk and want to run this application, even though I hate Java. And I believe on the PowerPoint notes that I uploaded on Edline that you can actually click on this directly from there and it'll take you to this page too. I think I did the hyperlink correctly. Alright, so here we go. On this you can add more charges. This one I only have 1 charge, and you can up the coulombs, the microcoulombs. You can see more and more field lines come in whenever you do a stronger electric field. You can also make it negative. But the cool thing about this one too, you can add in a second charge. And you can see how the electric field lines interact. So you can use this to compare. You can see the net force on each charge. You can see, all the other kinds of stuff. You can measure the electric field with like a 4 microcoulomb charge. And feel free to check out any of these other cool little applets over here. Back to the PowerPoint though. Get my pen ready. So electric field lines, when 2 charges are close together, they're going to interact. You can see here's the positive field lines coming out, and the negative field lines going into the negative one. So a lot of crazy things happen. They start bending and twisting and all kinds of crazy stuff. And here's what they look like if there's 2 positive charges. You see that they just don't run into each other. They're actually repelling, because we know that 2 like charges are going to repel each other. So we got this stuff repelling here. They form like a wall in between them because they don't get along. So electric field lines are actually the lines that indicate the strength and direction of an electric field. The more dense the lines, the stronger the field is. The electric field vectors are tangent to the curve. You can draw all kinds like circles in here, and they'll be like tangent to all these different curves. And here's another simulation for you. You can see, this one's a lot better than the other app. You can actually change the right-hand charge to be either positive or negative and see how the the electric field lines interact, and you can change the strength on the right charge too to see how they're going to interact. All kinds of crazy looking pictures. So if you ever forget what they look like, just click on the link in your PowerPoint's notes. So conductors, electric fields, under electrostatic conditions. Remember, electrostatic means the charges are still, static, still. So the electric field is 0 inside a charged conductor. This is how the cage demonstration at the Boston Museum of Science works. There's no electric field inside this charged conductor. I'll show a video of that in a second. Excess charge on an isolated conductor resides on the surface of it. So on that cage at the Museum of Science, all the charge is on the surface. There's none on the inside. It's all on the outside. That's why it's safe to be in there. And excess charge accumulates on sharp points. So if that was like a box that the person was in at the MOS, like there'd be more charge on the points than there would be on just the straight lines that make up the box. And the electric field lines meet the conductor perpendicular to the surface of the conductor. Like they shoot out normal to the surface wherever they're at. Here's a cool little video. I don't know why it's being all weird. Let's see if I can rewind this. There we go. So if you're ever caught in a lightning storm, where do you think the safest place to be is? If you said inside of a metal container, you would be correct, because all of the charges reside on the surface of the metal container. So all the charges are outside of this guy. There's nothing on the inside. So all the charges are out here, you're protected on the inside, there's no electric field, so the lightning can strike your car as much as you want. And it won't hurt you. Pretty cool. So as I said, where are you safe during a thunderstorm? In a car. You can go ahead and check that box off. And it's not because the tires, some people think, oh, because the tires are rubber, it's grounded. If you ever go to the MOS, they'll show you that that is not true. The electric charge will go right through a tire, so will lightning. So just be in your car, windows up, because, you know, it'll probably be wet and stuff like that. So why can you not get radio reception in a tunnel or a steel bridge? For the same reason. The charge resides on the outside of the tunnel, or the outside of the bridge, and it repels like all the other charges trying to come in. So you get no EM waves, electromagnetic waves, coming into the tunnel or through the bridge. Which field is stronger? Which one do you think? I'm going to say this guy because these lines are very close together, but these lines are very far apart. So that guy. Electric field for a point charge using this and Coulombs Law. If we don't remember what Coulombs Law is force equals K Q1 Q2 over R squared. I want you to prove this equation can also work to find the electric field, where Q is the central charge. So to do this, we know F equals all this stuff, and we know E equals F over Q. So what we want to do is plug Coulombs Law into the equation. Q1 Q2 over R squared. All of that over this Q prime. So your Q prime cancels out with your test charge over here, and we're just left with E equals K, and we're going to call Q the central charge, not the test charge. So one of these is central and one of these is test. We're calling Q2 the test charge. So this Q prime is the same thing as this Q2. And you're left with the R squared, which is the distance between them. So you've just done your first physics derivation. If you are brave enough to study physics in college, you'll do millions of derivations. None of them this easy. Example number 2, a test charge of positive 3 microcoulombs is located 5 meters to the east of a negative 4 microcoulomb charge. First, I'm going to find the electric force felt by the test charge. So to find force, we are going to have to do Coulombs Law. Force equals K, and K is 9.0 times 10 to the 9 newtons meters squared over coulombs squared times the 3 microcoulomb charge, 3 times 10 to the minus 6. Yes, you're going to have to convert these because if you don't, the coulombs here won't cancel out with the coulombs here. All this times 4 times 10 to the minus 6 coulombs. That's your negative charge. We can go ahead and make it positive though. It's not going to affect our answer here. We can make this positive because if we put our negative 4 one here, and here's our positive test charge, 3, the force, we're trying to find the electric force felt by the test charge. Since like things are opposites attract, it's going to go this way. We're just looking for the magnitude of the force. Over R squared, which is 5 meters squared. So you can see that the units are going to cancel out. These coulombs squared are gone with both these coulombs. That meters squared is going to cancel out with our meters squared. We're left with newtons for our force, which is good because newtons are force units. And you get 4.32 times 10 to the minus 3 newtons. B, find the electric field of that location. This is going to be easier. E equals F over Q, so our force is 4.32 times 10 to the minus 3 newtons divided by the positive test charge, divided by 3 times 10 to the minus 6 coulombs. I'm going to get newtons per coulombs, which are good because that's what we want for our units. And you get 1440 newtons per coulomb. And if I did this right, I did it right. And it's along the negative x-axis, which we can see here because we always choose positive x to be the right. And if it's located to the east of this charge, it's going to go in the negative direction because opposites attract. Example 3, if a test charge is moved to a location 3 times as far as its original location, how does the E field change? So we use that other equation that we did the derivation for, K Q over R squared. So in this case, we are making the location, the radius, the distance, 3 times as far as the original location. So we put a 3 here. And remember, all that is squared. So we have that 3 squared actually becomes 1 over 9 K Q R squared. So therefore, if we move the charge 3 times as far away from the original location, our electric field decreases by 1/9. Alright, so for the last example, I want you to calculate the electric field felt by a test charge located halfway between a charge of 1 coulomb and a charge of negative 3 coulombs. And these two charges are 2 meters apart. The first thing you want to do, you want to draw a little picture Here's your 1 Coulomb that's positive. Test charge, remember I said test charges are always positive. And then you got your 3 Coulomb guy right here who is negative. So -3. Nothing to convert here. They're already in coulombs. You don't have to do the micro stuff. Alright, so we want to find the electric field felt by this test charge here. So since this guy's positive and this guy's positive, force is going to be pushed that way because like charges repel. And since this guy's positive and this guy's negative, it's also going to be pushed this way because opposites attract. So what you want to do here is break this up into 2 steps. The test charge is going to feel electric field due to the first one, we're going to call E1, and electric field due to the second one, which we're going to call E2. So E1, we're going to use the equation KQ over R squared. K is our 9 times 10 to the 9th newtons meter squared over Coulomb squared, or Coulomb squared over meter squared, one of those two. Our Q here is going to be the charge on the positive guy, so that's just 1 Coulomb. And the distance between them is 1 meter because it says that the 2 charges are 2 meters apart and the test charge is happening between half of 2 is 1. So you get 9 times 10 to the 9th newtons per Coulomb. Now we're going to find E2 same way. K 9 times 10 to the 9th newtons meter squared over Coulomb squared. Charge on the second guy, which is -3. We're just looking for the magnitude though, so you just leave it as 3 coulombs. Same distance between them, 1 meter squared. And you get 2.7 times 10 to the 10 newtons per Coulomb. So the total charge here, the net electric field, is going to be E1 plus E2, which gives you 3.6 times 10 to the 10 newtons per Coulomb. That should be it. 3.6 times 10 to the 10. Cool.